So today we will be talking about OpenACC. So that's going to be the last lecture in the series of GPU parallelization lectures. So OpenACC is a framework that's used for utilizing the GPUs for accelerating or parallelizing your code. It's much simpler as compared to CUDA based kernels that we have been talking about. So there's an official OpenACC link that you can have a look at, which gives you the details about how to parallelize codes with OpenACC. So here's a sample code that we have parallelized using OpenACC. This is a Fortran code. We're back to Fortran now. So if you have a look at the lines which are in bold, they look very similar to what we had in OpenMP. So you can see that it says bang dollar ACC parallel loop and then some further details. So bang dollar ACC is like bang dollar OMP, parallel is like OMP parallel. So this is basically telling the compiler that you have to parallelize these loops that we have below. Loop means loop. So like in OMP we had an OMP parallel which simply created the threads, but if you have an OMP parallel do that would ensure that the iteration of the loop will get distributed among the threads. So that's exactly what the intent of this statement is. And collapse 2 is basically telling that you have do loops below this statement and go 2 levels down in this do loop. So there are 2 do loops, one is over I and the other is over j. So collapse 2 basically means that it will combine the iterations of both these loops. So if you have I going from 1 to n and within that j going from 1 to n, you have a total of n square threads that you want to create, because this basically is dealing with n square elements of the matrix C. So this collapse 2 is saying that you go down 2 levels into the do loop and whatever number of threads you have, you parallelize them into that many cores of GPU. So if I had only collapse 1 here, what it would have done is it would have gone only to the do I equal to 1 to n. It would have generated it would have generated n threads for this I loop. But if I say collapse 2, it generates n square threads for both I and j loops. So this is possible here because for every I you have j going from 1 to n and so on. So there is n square iterations here. And then there is this statement called present A, B and C, where A, B and C are matrices. So present means that before you start doing anything on the GPU, it's telling the compiler that these matrices A, B and C are already present on the device. Remember, device has its own memory. The architecture does not change, we are just changing the programming paradigm. So this is telling the compiler that the matrices are already present on the device, so there is no need to copy. If we don't specify this statement, it may happen that it may try to copy the information first depending on the kind of compiler you have, and that would take extra time. So if you already know, it's always recommended that you copy the information manually, but this statement explicitly tells they are present, so there is no need to copy it from the host to the device. And then you have bang dollar ACC end parallel. So you see that it's much simpler to use OpenACC as compared to CUDA, for example. So that will be a first level choice if you have a big program and you want to parallelize it using this kind of an approach of a parallelism approach which does not require to reorient the whole program. Again, it's like OpenMP. So if you compile with a flag for OpenACC, it compiles for OpenACC. If you do not have that flag, you will simply say G Fortran and compile this, it will compile it as a normal program because you have an exclamation here. So, these lines will be ignored as comments if you do not specify the ACC flag in the compiler step. Now, there is another way to program parallelize things in OpenACC, that is using the kernels clause. So, in the kernels, if you look at the code this time, it is the same intent, it is bang $ACC, instead of parallel you have kernels now, and then you say present A, B, C. Now, kernels is more higher level and more automatic. So, in the sense that if you do not want to put too much effort, you would simply say ACC kernels and that will do the job. So, it will try to figure things out automatically by itself as to how many loops should it go down into this so that it can safely create parallel threads and so on. So, kernels is a more smarter command in OpenACC as compared to parallel. So, if you want better control over things, you are experienced, you will go for the parallels, ACC parallel. If you want a very quick parallelization, you will simply say ACC kernels, and again present here means that A, B and C are present on the device. So, before that this is more complete program in this case, you would have said ACC data, which is basically telling that it is an ACC data statement. So, it is about copying something. So, it says copy in A and B. So, that means A and B will be copied from the host to the device before the program starts, and copy out C means when the execution is completed, C will be copied out from the device onto the host. In this case, you do not need to copy in C because C is simply going to store the results. So, there is no need to copy, just create that and that will get created automatically on the device. But you have to copy it out because when you try to print the value of C later in the program, that has to be available on the main memory of the CPU. So, now you may think that there are many things that we are not controlling, for example, synchronizations and so on. So, this is all embedded into the compiler. Now, this may do expected things or sometimes the things may be unexpected. So, synchronizations will happen whenever it is most logical for them to happen as per the compiler's design. So, again there is a trade off. If it is a simple program, you simply want to parallelize the large do loops that you have like in OpenMP. So, you simply use OpenACC and that does the job. I mean, if you have a good GPU card and you quickly want to parallelize something without spending too much time on the program, then you can use OpenACC, and it has been used successfully. So, it is not that nobody uses that. In fact, some people tend to use it more as compared to using CUDA, because CUDA, if you have a program which is written over last 10 years, converting that to a CUDA parallelized program is a huge job. And the main worry is you may end up breaking something. How do you test everything that has been developed by 20 different people over the last 10 years? So, the easiest thing, the safest thing in this case is to use OpenACC and parallelize the loops in a fine grained fashion. So, let us look at another example. So, on the left we have vector addition where A and B vectors are added into the vector C. On the right we have vector addition with OpenACC. So, let us look at the code. Again, these are Fortran codes. So, you have a module called vector addition. In that you have a subroutine which is vector addition, which takes A, B and C and also the size of the vectors. These A, B and C are real double precision, and the dimensions are single dimension. So, they are vectors, and then you simply say do I going from 1 to n, C of I is equal to A of I plus B of I. So, if you look at this program, you would know that this is, if n was a very large number, this is the operation that you would want to parallelize. It is an embarrassingly parallel problem. I mean, the different elements of C can be calculated in parallel without affecting each other. So, all I have to do is I have to parallelize this. So, I know that I have to have some OpenACC call before the do loop, and if you look at the parallelize code, that is exactly what is happening here. The only line that is different is this bang $ACC which is being put before the do loop. So you say bang dollar ACC kernel's loop, just as we showed in the last slide. Then you have combined your data statement with the ACC statement. So you say copy in A and B and copy out C. Okay. So before this ACC kernel threads get created by ACC, it will copy A and B from your host to the device. It will do the computations on the device, calculate C on the device, and then copy out C from the device back to the host. And that's it. You have bang dollar ACC end kernels, and this compact change will help you parallelize your code for a large value of n on the GPU. So there is always a confusion between kernels and parallel. So this is a very good book. In fact, I have used this book to learn ACC, OpenACC. So you should definitely refer to this book. I will put this book on the Google Drive for the course. So there is one paragraph I have quoted from this book. It says, whereas the kernel's directive place the onus on the compiler to generate the correct code, the parallel directive put the onus on the user to spell out what to parallelize and to ensure that correct code was generated. So as I said, kernels is more automatic. So if you using OpenACC initially, you will end up using kernels. That lets the compiler decide how to parallelize code and create threads. Whereas if you have more understanding, or if you once you have written a kernels based code, now you can go back to it and slowly use OpenACC parallel, because that gives you more control over things, but that also makes the things more predictable. So let me show you an example of a situation where things will not work as intended. So this is where putting ACC kernels will actually do the right thing. But if you do not have understanding properly of ACC parallel, you may end up doing something which is not the correct thing. So let's say we have ACC parallel. It's like OMP parallel. So when you say OMP parallel, it generates the threads. Okay. So ACC parallel generates the threads, and then you have an ACC loop. So ACC loop is for this do loop. So this has 1000 iterations. So it creates 1000 threads on the GPU, and they get executed in parallel. But you also have an ACC loop again. This has 1000 threads as well. So what it does is it's asynchronous. So what it does is when it sees this ACC loop, it generates 1000 threads, but it does not stop. I mean, the host code goes again here. It sees another ACC loop. It generates 1000 more threads and runs them in parallel. So it may happen that these 1000 were running already on GPU, and these were also sent to the remaining threads on the GPU, the remaining cores on the GPU. But that is not what you want, because here what you are doing is you are putting A equal to B of I, but here you are changing the value of B. So if it happens that while before you have actually put in the value of A, you change the value of B, the code will be having a different result as compared to if you had run this in serial, right. So the intent that you had was that you want to execute this in parallel, but once this is done, you want to synchronize all the threads, or you want to wait here until this loop is finished, and then you want to parallelize this. So for that, what you have to do is you have to put an ACC end parallel here. So when that ACC parallel is finished, that's where all the threads are again joined, and then you create new threads once this first execution is completed. Okay. So this is just an example showing you that ACC kernels is always a safer choice in the beginning. So ACC kernels would have given you the right thing, but ACC parallel with ACC loop for these two loops is not the right approach. You can also put a barrier if you don't want to end the parallel block and start it again. You can have an ACC barrier here, like you had OMP barrier. So that barrier will ensure that all the threads finish in this do loop, they report to the barrier, and then they proceed further, and then you have this loop happening after the first do loop. Is that clear? So, just like we had levels of parallelism in our CUDA, where we used to call these blocks, then we had warps, and then we had threads, right. Each block had a few number of warps. Each warp had around I think it had 32, as we discussed up till now. The standard is 32 threads in a warp, and well, you have some threads in the warp, and all these threads in a warp, they work in an SIMD fashion. So, they are in lockstep, so they are executed at the same time unless there is a control divergence happening. So, here in OpenACC we have I mean it's the same thing happening, except that we have a different terminology. So, there is something called a worker, which is basically the same as what you had warp in OpenACC. So, a warp in CUDA is a worker in OpenACC. Okay. So, these are terms that you should understand. Then inside a warp you had threads. So, we call I mean sometimes it is a bit confusing. So, sometimes we call the warps as threads, vectors. So, you will have a vector of threads working. So, we will simply use the word vectors, and then like you had a block in CUDA. Remember, you generated you had blocks of threads. So, you have to decide the number of threads per block. So, these blocks in OpenACC are called a gang. It's a funny terminology that you have a gang of workers working together. Okay. So, this is in this picture you can see you have multiple threads working in a lockstep like in a vector, and you could also call it a worker which has multiple threads in it, and then you will have a whole block or a whole gang where multiple workers or multiple warps work together. Okay. So, I mean very similar terminology. So, like in CUDA, here also we can specify the number of threads per block and so on. So, I mean so the vector length is basically number of threads per warp, and number of gangs is the number of blocks you have. So, you can specify this information in or if you do not specify it like we have been doing till now, the compiler automatically decides that. So, it is not necessary like you had in CUDA kernels, you had to specify this information, but here the compiler will figure it out by itself if you do not specify this information. So, the number of gangs, the number of threads in a given vector. So, vector length or this worker size, number of threads in a worker is used interchangeably. Okay. They have a subtle difference, but we will not worry about that for now. So, you specify the number of threads per block and the number of blocks. Okay. So, the number of gangs and the number of threads per vector. Next is reduction. So, like in OpenMP we had reduction, we have reduction here as well. So, let us look at this loop where you are basically adding all the elements of a vector called data. So, you start with the total, and each I mean if this was serially executed, then a total will get incrementally you will keep incrementally adding the elements of data into the variable total. So, if you have ACC where each thread is handling one element of data, so then their total, so total is a variable which exists on all the threads, each thread's total will have contribution from one element of data, right. So, all they have to do is now they have to reduce that using the addition operation and combine all the totals. So, this is where it is very similar to OpenMP, ACC parallel loop reduction plus colon total. exactly the same as OpenMP. In fact, many cases what happens is people parallelize the code using OpenMP first, and then they simply modify the OMP statements to ACC statements, making some other changes as well. So it's basically very similar to OpenMP. So you would write an OpenMP parallelization first, try it on your CPU cores, even if you have a few of them, and then you proceed further to convert that to an ACC parallel code. So how do you compile this code? Well, there are different compilers available. So we have different. So this is NVIDIA PGI compiler. So I think now for Linux it's available for free. You have a GCC compiler, which is the GNU open source, and then you also have some research based compilers like by Cray and others. So this OpenACC has been developed in the research community extensively. So there are some research compilers available as well. We will demonstrate to you the PGI compiler, which is the NVIDIA PGI compiler. So what you have to do is, like you had in OpenMP, you had the -f OpenMP flag to tell the compiler that compile this program using f OpenMP. So you have to give this -acc flag in the PGI compiler, or the f OpenACC flag like you had in G-Fortran. So this is GCC, so very similar. So what this compiler flag would tell the compiler is that this code has to be compiled using OpenACC, and then you can have some additional flags which are optional. Is you can specify the target architecture, like with CUDA we specified that it's the compute capability 8.9. So I had SM_89. So this is something similar. So you specify the architecture so that the compiler gets understanding of how the architecture looks. But if you don't specify it, it's smart enough to figure out by itself what architecture you're using and compile the program according to that. Then you can specify some extra Minfo accel. So that basically if you compile with Minfo accel, what it does is because it's doing things smartly, it tells you that what steps it followed. So for example, here if you look at this text here, so we compile this code using Minfo accel. So it says that number 40 generating implicit copy in data. So it's copying in data vector. Then it checks the loop is parallelizable, accelerator kernel generated, generating Tesla code, and so on. So it's doing some further operations. So basically it's telling you step by step as to what it is doing, how your kernel statement or whatever statements you've written in the code with $ACC, how they're interpreted, and you can check if that is exactly what you intended or not. So that's basically some help to the user to understand if their directives using their ACC directives were interpreted the way they wanted or not. So before I actually demonstrate to you how to parallelize, to compile and if possible run the code on Param Himalaya, let's have a look at a bigger code which gives you an impression as to this is really a usable thing. So on the left we have a serial code, on the right we have the same code which is parallelized using the ACC directives. Here you don't need to understand the code as such, but just for reference, this is a code which is used to calculate the solution to the Laplace's equation, which is used in many modeling situations where you will be, for example, heat diffusion and so on. Here actually it's used for energy equation for heat diffusion. So if you want to calculate the temperature in this room, you will want to solve the Laplace's equation if it's purely based on diffusion or conduction, whatever you want to call it. So this is now let's not worry about the application, but let's have a look at the code. So you have a do while which is basically checking for convergence. So it's solving some, I mean in this room if you want to solve for temperature, you'll start with some initial temperature and then you will solve the code. In reality, if you think about it, if I make a sudden change to the weather, it will take some time for that effect to reach a steady state. So that after that no temperature in the room will change further because of these boundary effects. So this is simply checking for steady state. Okay. Then you have these two do loops, which is basically taking j from 1 to width, I from 1 to height. So it's basically telling that you have a two-dimensional situation, not a 3D room like this, but a two-dimensional plate, and you are solving for temperature at different grid points on the 2D plate. So these two do loops are simply like you had to refer to the elements of the matrix C. So you can definitely parallelize this, right? And then if you go further to this next set of do loops, here again you see that you have two do loops. One is going from j to 1 to width, the other is from I equal to 1 to height, and then you refer to each and every element of the temperature somehow. So again this seems parallelizable. So there are two nested do loops that I can potentially parallelize, and if your width and height are very large numbers, then you will see that there is a lot of work to do in these do loops. So it's definitely worth parallelizing them. Now let's look at the corresponding parallelized code using OpenACC. So you see that in this nested do loops, we simply put an ACC kernels here. That's pretty much it. And then you have an ACC end kernels, and this will do the job. It will automatically figure out that you have nested do loops here, which can be parallelized. It will generate these width times height number of threads and send them to the cores of the GPU. Similarly, for the other, you also have a similar ACC kernels and ACC end kernels. So that's what you'll do first. But then now you start thinking about copying the data first, because we didn't copy the data from the host to the device. So when should I do it? Well, what data do I have? I have two matrices here. One is temperature matrix, which is storing the temperature at the current time, and then you have temperature underscore previous, which is storing the temperature at the previous time. Okay. So before you start this execution, this complete execution in this main do while loop, you will have some initial temperature. That's your initial condition. So you have to specify that. So initial condition will be set by the user. This is not the complete code, so you don't understand that, but I am telling you that temperature underscore previous is something that will be initialized in the beginning, and then you will keep using it again and again. So the code needs to read this temperature underscore previous first. So that has to be a copy. So this ACC data copy statement says that temperature underscore previous will be copied before you start this. So at this step, this matrix gets copied from the host to the device. But temperature does not need to be copied, because temperature is only used as an intermediate. I mean, it will be calculated on the device. So you simply say create temperature. Now create temperature means that temperature matrix gets declared on the device. So the device will allocate some memory to temperature as well, but temperature previous will be copied. So the memory will be allocated on the device, and it will be copied from the host to the device as well. So that sorts of helps us, because now this statement says that for this whole now you have an ACC end data. You can see that here. So between whatever is, so this ACC data and this ACC end data match with each other. So what that means is that this temperature and temperature previous will exist on the global memory of your GPU for this whole block. It's not that this will temperature previous will get deallocated somewhere in the middle. So this is the block for the scope or the lifetime of these matrices on the global memory. But there is also one other thing happening in the code. If you have a look at it, what we are doing is we have lots of iterations, right? So each step in this main do loop is an iteration. There will be lots of iterations happening, because the temperature will slowly go from initial temperature to the steady state temperature that you want to calculate. So, we have a track progress subroutine that basically prints the value of temperature, or it plots it, whatever, it does some printing on the screen. But what happens is that this temperature matrix is sitting on the device, on the GPU memory, and this statement track progress, this subroutine track progress, it is being called by the host or the CPU. So, if you call it, now temperature which which may have a copy on the host as well, is empty. When you run the code, the temperature matrix on the GPU memory is getting updated. So, whenever you want to print it, you have to explicitly copy the data from the temperature matrix on the device to the temperature matrix on the host. So, just before this track progress subroutine, you have an ACC update host. So, what that does is, just before this, it copies the temperature from the device to the host, so that you have the latest value of temperature matrix available on the host, and you can print it now. If you did not have it, it would have happened that you would have printed zeros all the time, and that is a bit confusing. But if you have an ACC update every time outside this if loop, for every iteration you are copying temperature, that slows your program, because there is no need to copy the temperature matrix every time from the device to the host in every iteration, because you only want to copy when you want to use it on the host. Okay, so you keep this ACC update inside the if condition, and this if condition basically is checking for every 100 iterations. You are doing a remainder, say mod operator in iteration comma 100 is equal to 0. That means after every 100 iterations you want to update the temperature on the host and print the values on the screen. So, you see that we have a working serial code that we were able to parallelize using OpenACC very quickly. So, my recommendation to you will be, if you are starting from scratch and you know that you will be parallelizing for a GPU, it is okay to develop a CUDA code, but if you have already developed a code, or if you have a working code available to you and you want to parallelize it, it is not that difficult to parallelize it using OpenACC, especially because it is very similar to OpenMP, and OpenMP is something that is very easy to use with fine grained parallelism, where you have these do loops that you want to parallelize. And now if you start comparing with CUDA, CUDA is a bit more intense. You have to write special kernels for CUDA, and then they have to be generated and so on. You also have to think about the memories and so on. So, of course, things can go wrong with OpenACC as well if you try to, if it is out of memory and so on, but it is always worth, even if I can do profiling in the code and I see this is the most expensive loop in the code in terms of the elapsed time, I can simply try to parallelize that without touching anything else. Okay. Any questions? So, that is the end of our discussion, which is the part 1 of today's lecture, that was on OpenACC, but that concludes our discussion on GPUs. So,